Hello, in this video I'd like to talk about a major consequence of the negative result to Hilbert's 10th problem. Richardson's theorem is about symbolic algebra. Given two algebraic expressions, two formulas we can write out or encode on a computer, can we determine if they represent the same function of their variables? One can imagine this being really important, for instance, if you're coding an online homework system. You need to check if the answer a student types in is equivalent to the answer in the database, although they might disagree substantially in their presentation. I've seen this before, particularly with integration problems. If you approach a problem in a completely different way, you'll get an answer that's still equivalent, but you'll get an answer that's potentially very different from the answer that I was expecting to see. Well, it turns out that this problem of checking equivalence between algebraic expressions is equivalent to determining if Diophantine equations have solutions, which we've shown previously is equivalent to solving the halting problem. This is a really fun type of math, focusing on doing some deep mathematics about really basic topics. In this case, just basic pre-calculus, basic manipulating expressions. Let's be formal about this. I'll call an algebraic expression Richardson if it is built up out of variables, so as many variables as we like, constants representing the rational numbers. We'll have a constant for pi as well. I'll link you down below to a paper where it turns out you don't actually need the pi, but we'll use it in this video for now. Addition, subtraction, and multiplication, so we'll avoid division so we don't have to worry about division by 0, the sign function, and the absolute value function. And the question we're going to ask is, given two such expressions, are they equal no matter what real numbers we plug in for each of the variables? Are they identically equal? And you might say, hey, hold on, you're about to do something tricky with the absolute value function. It's not particularly surprising that you can do something tricky with the absolute value function. And yes, that's exactly what we're about to do. But understand that the absolute value of x is the square root of x squared. So if we want to reason about expressions with square roots and signs in them, we're going to have to at least be able to reason about expressions with absolute values and signs in them. And actually, we're also about to do something tricky with the sign function. It tends to be the case that with these sorts of decision problems, working with real numbers is easier than working with integers. For instance, determining if multivariable polynomials have real roots is decidable, while determining if multivariable polynomials have integer roots is undecidable. On the surface, it looks like this problem here is about real numbers, determining if two expressions are equivalent regardless of what real numbers we plug in. But actually, since we have the sign function and pi, we can talk about the integers. A number x is an integer if and only if sign of pi x is 0. So we can talk about the integers and we can talk about polynomials, and this will allow us to make use of the negative result to Hilbert's 10th problem to create some undecidability. As is common of these sorts of things, it'll be convenient to switch our perspective back and forth between asking if two Richardson expressions are equivalent and asking if their difference, which is of course another Richardson expression, is identically 0, is always 0 no matter what values we plug in for the variables. To put this problem in context, let's compare with the problem of polynomial expressions, the sorts of expressions that expand out to polynomials. Formally, a polynomial expression is built up out of as many variables as we like, constants, addition, subtraction, and multiplication. And again, we're interested in determining if two expressions represent the same function of their variables. And in this case, any college algebra student should be able to figure out if these expressions are equal. Working from the inside out, they just expand to polynomial canonical form, that is, sums of products of some coefficient times some variables to various powers. So somehow, adding in sign and absolute value turn this problem from really straightforward to uncomputable. It's always a nice treat when a paper explains the intuition behind a proof, and Richardson's paper goes so far as to give us a simplified preview of the full proof. which looks something like this. The first step is to focus not on determining if two Richardson expressions are equivalent, but on determining if an inequality involving Richardson expressions has real solutions. So the first step is going to be to show that being able to determine if inequalities of Richardson expressions have real solutions, if being able to determine that allows us to determine if Diophantine equations are solvable, which again, remember, is undecidable. So let's start with some polynomial p in, let's just say x and y for now, with integer coefficients. We should imagine p of xy equal to 0 as some sort of Diophantine equation corresponding to some sort of really difficult halting problem. In reality, p will have a lot more variables. If you want a difficult halting problem, as far as we know, you might actually need at least 9 variables, although this is very open. There's still actually a bunch of 2-variable Diophantine equations that we don't fully understand. Let's also assume that p of xy is always non-negative. The coefficients in p will allow those to be negative, but for any values of x and y, plugging them in will give us a non-negative number. You can turn any polynomial into such a polynomial just by squaring it, so we haven't really lost any generality. Next, let's imagine that k is some huge polynomial in x and y. It has really large values and is rapidly growing. Now let's define f of xy as k of xy times p plus sine squared of pi x plus sine squared of pi y. I claim that there being real values making f of xy strictly less than 1 will be equivalent to there being integer values making p of xy equal to 0. So first of all, one direction, suppose that p of xy equals 0 for some integer xy, right? Suppose that there's a solution to our Diophantine equation. Then those x and y, if we plug those into f of xy, they'll of course make p of xy equal to 0, and they'll also make these sine terms equal to 0. So those x and y will be a solution to f of xy is strictly less than 1. On the other hand, if f of xy is strictly less than 1 has a solution, then this term here is going to have to be very small, since k is very large. So p of xy is going to have to be small. It's going to have to be less than 1 and close to 0. These sine terms are at least 0 because they're squared, and p is at least 0. So what we have here, this sum is going to be a partition. We can't allow one of the terms of this sum to get large by having another term be negative. It's just the sum of 3 non-negative things, and together that sum has to be a pretty small number, like less than 1 over k. And by the same reasoning, these sine terms are going to have to be close to 0 as well. So x and y, the solutions that we found to our inequality, are going to have to be close to integers. They don't have to be integers, but they have to be pretty close to integers. So if we round x and y to the nearest integer, then probably won't change the value of p that much. So p of those rounded values is going to have to be small. It's going to have to be less than 1. But since p has integer coefficients, when we plug those rounded values into p, we're going to get an integer. And the only suitable small integer will be 0, right? The only integer that's non-negative and less than 1 is 0. So under the assumption that f of xy is strictly less than 1 has a real solution, p of xy equals 0 will have an integer solution, completing the proof that these are equivalent. But that's really only the first part of the proof. We're going to have to switch from reasoning about if Richardson inequalities have solutions to if two Richardson expressions are always equivalent. And this is where we do the tricky bit with absolute values. So again, we're not really interested in talking about if an inequality has a solution. We want something like, does this always happen? Are these two expressions always equal? Whereas an inequality having a solution is, does this ever happen? Does there exist solutions? So we're going to have to negate somewhere. Instead of talking about there being an example, talking about there not being a counterexample. We also need to switch from talking about inequalities to talking about equalities. So here's where we do the tricky thing with absolute values. F of xy is strictly less than 1 has a solution if and only if the absolute value of f of xy minus 1 and f of xy minus 1 are not identically equal, or equivalently that their difference isn't identically 0. So we take our expression for f, plug it into the difference between these two, and check if the result is 0 for all values of x and y. And that will tell us if our original Diophantine equation does not have a solution. This negation here, this switch from looking for solutions to an inequality to seeing if two expressions are not identically equal, took me a while to wrap my head around. For all of these difficult problems, there's the easy half and the hard half. For instance, when we're talking about Diophantine equations, it's really easy to prove to someone that an equation has a solution. You just tell them the solution. And if we know there's a solution, we can safely go out searching through all possible tuples of integers until we find it without worrying about never halting. The hard part is if there is no solution to the Diophantine equation. In that case, our search will never terminate. We'll be stuck not knowing if there genuinely is no solution, or we just haven't found it yet. Of course, some Diophantine equations don't have solutions for clear reasons, but there isn't a general algorithm for determining this. And again, this corresponds to the situation with Turing machines. It's easy to verify that a Turing machine halts. You just run it. If you just list out the states of the machine at any one particular time from when you started to when it halts, that is itself a proof that the Turing machine halts. If the Turing machine doesn't halt, on the other hand, it may be for easy-to-prove reasons, but it also might not be. And no general algorithm can help us in all cases of Turing machines that don't halt. And now in the Richardson expression case, it's actually showing that two expressions are not identically equal to each other, that's the easy bit, and showing that they are identically equal, that's the hard bit. Specifically, if two Richardson expressions are unequal, they actually have to be unequal for some rational assignment of their variables. Right? Richardson expressions are continuous, since they're composed of continuous things, addition, subtraction, multiplication, sign, and absolute value. And if two continuous functions are equal at all rational points, since the rational points are dense in Rn, the functions must be equal everywhere. Contrapositively, if our two functions are unequal somewhere, they must be unequal at a rational point. If it weren't for pi and the sine function, it would be super easy at this point to verify that our two expressions were unequal at this particular rational point. We could just plug in the rational values for the variables and do basic calculations with rational numbers. It's a little bit trickier when we introduce pi and the sine function. We need to use approximation techniques to calculate the two sides of the inequality to a level of precision that's good enough to verify that the two sides are different. And just like how we have some heuristic techniques that can sometimes show that a Diophantine equation has no solution, or a Turing machine doesn't halt, there are some heuristic techniques using algebraic rewriting rules that can sometimes easily show that two Richardson expressions are equivalent, but they can't handle all cases. So we've seen how we can go from determining if Richardson inequalities have solutions to determining if Richardson expressions are equivalent, but first, we're going to have to get from solving Diophantine equations to solving Richardson inequalities. I've given you a sketch of the proof here, but there's lots of details we're going to have to fill in. First, nothing weird happens if we go from two variables to lots of variables. That was just for notational convenience. We're also going to have to figure out how to determine our function k. And to do that, we're going to have to reason about how the value of p at one point is related to the value of p at a nearby point. Specifically, our goal is to connect the value of p at some real number point and p at the nearest integer point. To do this, we're going to want to use this consequence of the multivariable mean value theorem. I'll talk about this more in a bit, but for now, notice that we're bounding the difference between p at one point and p at a nearby point in terms of partial derivatives of p evaluated somewhere between our 2 points. These partial derivatives are polynomials, and we'd like some sort of upper bound on them. But note that we don't want an upper bound on these partial derivatives at lowercase x or uppercase x. We want some upper bound on these partial derivatives at c. And we don't really know what c is other than the fact that it's somewhere between lowercase x and uppercase x. So really what we want is some upper bound on these partial derivatives on all points nearby lowercase x. So given a multivariable polynomial q, and you should be thinking of these partial derivatives here, we want to find some polynomial r such that not only is r at any one particular point larger than q at that particular point, but also larger than q at nearby points, if we vary any of the inputs by up to plus or minus 1. And we'd also like to ensure that r is always at least 1, just to make some things work out nicely later on. Such a polynomial r exists for any polynomial q, and whenever this sort of upper bounding happens, we call r a dominating function for q. We're going to use these dominating functions as upper bounds on the partial derivatives of p, which in turn will allow us to upper bound the difference between p at lowercase x and uppercase x at our nearby points. So first, let's show that we can actually find these dominating polynomials. Right, so given a multivariable polynomial q, we're going to want to be able to find some multivariable polynomial r that dominates it. The proof is by induction on the construction of the polynomial. If we have a constant polynomial, the absolute value of c plus 2 will dominate it. My instinct would be to just add 1, but the plus 2 is necessary to make sure that the polynomial is larger than 1. If we have just a lone variable x, then x squared plus 2 will dominate it. If we already know dominating polynomials for p and q, we can find a dominating polynomial for p plus q just by adding them together. And this polynomial will also dominate p minus q. And finally, to dominate p times q, you just take the product of their dominating polynomials. These recursive cases being nice actually makes this a fairly straightforward process. Take your polynomial, turn all the minus signs into plus signs, replace all the constants with those constants plus 2, and replace all the variables with those variables squared plus 2. If you look back at the original Richardson paper, it doesn't actually use polynomials here. It was a bit more than a year after Richardson's paper was published that Matyasevich proved that the Fibonacci numbers were Diophantine, completing Robinson's proof that exponentials were Diophantine. At the time, it was only known that exponential Diophantine equations were undecidable, a result due to Robinson, Davis, and Putnam. And so the role of Diophantine equations as being undecidable was actually being played by exponential Diophantines in the original Richardson paper. So instead of talking about polynomials and dominating polynomials, it was talking about exponential polynomials and dominating exponential polynomials. But now that we have the negative result to Hilbert's 10th problem, we can simplify the proof to just talk about polynomials. So again, recall that our goal was to connect the values of p at 2 nearby points, to say that they're not too far apart, and this multivariable mean value theorem allows us to do that. This might not be the statement of the multivariable mean value theorem that you're used to, so let me show you the proof. Consider the straight line path between our 2 points, lowercase x and uppercase x. Right? This vector function h of t takes in a real number t and outputs a point that's t% of the way from capital X to lowercase x. And you can check that. If you plug in 0, you get capital X. If you plug in 1, you get lowercase x. And the function changes by the same amount whenever you change t by some amount. Now let's take our h and plug it into our polynomial p, and we'll call that function g of t. So this is what it looks like all expanded out. These are the values of our polynomial along this line from lowercase x to uppercase x. Now, despite having a multivariable function inside of it, g of t is just an ordinary function from reals to reals. So we can apply the single variable mean value theorem to conclude that the average rate of change of g between 0 and 1, that is just g of 1 minus g of 0, that is p of lowercase x minus p of uppercase x, is g prime of c for some c between 0 and 1. And by the multivariable chain rule, this is the partial derivatives of p at h of lowercase c, which I've denoted capital C, times the components of the derivative of h. We then take the absolute value of both sides of this equation and then toss in a few more absolute values. Might make the right-hand side bigger, and we get the inequality that we were trying to prove. Let's zoom out again. One of our major goals was taking an integer polynomial p and translating it into a Richardson function f, where p equals 0 has an integer solution if and only if f is strictly less than 1 has a real solution. And I roughly sketched out how we were going to get that f function, but let's talk about the specific details. We'll start by picking some polynomials k sub I that dominate each of the partial derivatives of p. Recall that this means that at any point, k sub I is going to be larger than the ith partial of p, not just at that point, but also at any nearby point, if we wiggle each input around by up to plus or minus 1. Then define f to be n plus 1 squared times p plus the sum of sine squared terms times k sub I squared terms. Of course, if p equals 0 has an integer solution, then this makes f equal to 0, so f is strictly less than 1. On the other hand, suppose that we have some real numbers, x1 through xn, that make f strictly less than 1. We'll want to show that when we round those numbers to the nearest integers, that makes p equal to 0. Rewriting our inequality a bit, we get that p plus the sum is strictly less than 1 over n plus 1 squared. Since each term in this sum is non-negative, remember that we assume that p only spits out non-negative values, each term in the sum has to be less than 1 over n squared. This includes p, and we'll actually just need that p is less than 1 over n plus 1. And similarly, the square roots of the terms in the sum also have to be less than 1 over n plus 1. Now I claim that if we round each of our x's, we get a point where p is 0. Remember that I'm using bracket notation to indicate that I'm rounding a number. By the multivariable mean value theorem, p at these rounded values is less than p at our original point plus the sum of how much we rounded by times the partial derivatives at some point c between the x's and the rounded x's. Since the k sub I dominate these partial derivatives, their values at x will be at least the value of the partial derivatives at c. We can then replace the distance rounded by the absolute value of sine pi x sub I. As we can see in this graph here, that's only possibly going to make the value larger. The absolute value of sine pi x is always greater than or equal to the absolute value of the distance that x gets rounded when we round it. Now, each term in this sum is going to be something that we've shown to be strictly less than 1 over n plus 1. And when we add up these n plus 1 terms, we get 1. So putting it all together, we're able to conclude that p at these rounded points is strictly less than 1. But p is an integer polynomial that only spits out non-negative values. So its output at this integer point has to be some non-negative integer strictly less than 1. And there's only one such integer, and that's 0. So p at this rounded point has to be 0. And that completes our proof that p equals 0 having an integer solution is equivalent to f being strictly less than 1 having a real solution. And then the tricky bit with absolute values is exactly the same as I showed you before. We can turn the question of if f is strictly less than 1 has a solution to is this expression not identically 0? Let's do an example. Suppose we're interested in finding if the Pell equation, x squared minus 3y squared minus 1 equals 0, has integer solutions. First, we need to make sure our polynomial only outputs non-negative values, which we can do by squaring it. Call this polynomial p. We then take the partial derivatives of p, so that we can find dominating polynomials for those partial derivatives. Again, all I'm doing is turning the minus signs into plus signs, adding 2 to all the constants, and replacing each variable with that variable squared plus 2. So 4x cubed becomes 6x squared plus 2 cubed, negative 12xy squared becomes positive 14x squared plus 2 times y squared plus 2 squared, and so on and so forth. And then we can define our function f as n plus 1 squared. N here is the number of variables, which is 2, times p plus these sine squared k squared terms, which expands out to this. It's really hard to visualize this function in 3D. If we plug in 0.1 for x and y, we get about 200,000 because there's just so many factors in this expression trying to make the function large. So I've had to take the log base 10, and what you see here are the results. If you look at all of these spikes happening in the integer grid, what that is the sine squared terms keeping this function far away from 1 if x and y aren't really close to integers. You can also see 10 of these spikes where the graph drops below the origin. That is, the function drops below 1, since the log of 1 is 0. And actually at those points the graph has a vertical asymptote. The value of our function f is 0, and the log of 0 is negative infinity. And here we can see that these points correspond to integer solutions to our original Pell equation. So we have what we were looking for, a Richardson function that is less than 1 only when we're close to a solution to our original Pell equation. Specifically, if you have a value where this function f is less than 1, if you round the coordinates, you get a solution to the original Pell equation. And again, by pulling off our absolute value trick, we can create a function that is non-zero only when our function f is less than 1. This function being not identically 0 is an assertion that there are values where f is less than 1, and thus solutions to our Pell equation. So that's Richardson's theorem in the multivariable case, but what about the case where we only have one variable? If we have an integer polynomial p of x with only one variable, it's actually really easy to determine if it has an integer root. There are various techniques to do this, but my favorite is the rational root theorem. Specifically, if there's a rational root to some sort of single variable integer polynomial, then it must be of the form some factor of the constant term divided by some factor of the leading coefficient. For any integer polynomial with non-zero constant term, this gives us a finite list of possible solutions to check. The polynomial might have other irrational roots, but if it has a rational root, it must be of this form. And if it has an integer root, then q must be 1. So really we're just looking for divisors of the constant term. So for instance, if we want to check if 2x cubed minus 3x squared plus 10 equals 0 has an integer solution, we just need to try plugging in the various divisors of 10 into our polynomial. Negative 10, negative 5, negative 2, negative 1, 1, 2, 5, and 10. If any of these give us 0, we have our solution, and if not, there's no integer solution. So it's really only when we get to the two-variable case where things start to get interesting, and there are a number of two-variable Diophantine equations of interest. We don't really know exactly when things start getting really interesting, that is, when we start getting Turing completeness. Maybe it just takes two variables, maybe we need as many as 9, we don't know. So one might ask, what happens to Richardson's theorem if we only have one variable? If we had an undecidable single variable Diophantine equation, our procedure from before would translate it to a single variable Richardson expression that was undecidable if it was identically 0. But we don't. Single variable Diophantine equations are easy, as we've seen. So does that mean that determining if a single variable Richardson expression is identically 0 or identically equal to another Richardson expression? Does this mean that that's easy? It actually doesn't. And the trick to showing this is going to be finding unpairing-like Richardson functions. Suppose we had Richardson functions L and R such that all possible pairs x, y were L of t, R of t for some t. That is, we could use a single real number t to encode the pair of real numbers x and y. Then looking for a solution to f of xy is strictly less than 1 is equivalent to looking for a solution to f of L of t, R of t is strictly less than 1. So looking for solutions to a single variable inequality is as hard as looking for solutions to multivariable inequalities. And we can again apply the absolute value trick to turn this into a question of whether two single variable expressions are equivalent. There's just a slight problem. Such functions L of t and R of t would give us a space-filling curve. And I don't think we can have a space-filling curve with such nice formulas, with Richardson expressions for their formulas. But we can have a curve that gets arbitrarily close to any point in space, and that will suffice. Richardson gives us the example of functions x equals t sine of t and y equals t sine of t cubed. I'll call these functions L and R respectively. As we can see, this gives us a parameterization of a curve that seems to be painting in the entire plane. As we go forward in time, the curve covers more area vertically and horizontally, and the oscillations get shorter and shorter to more thoroughly fill in the area covered. You should ignore the graphical artifacts here. It turns out this sort of function is really hard to graph to pixel-perfect accuracy. And again, this graph won't be able to reach exactly any point in space, but it will get arbitrarily close to any point in space. In fact, Richardson claims something slightly better than that. Given a delta and a point xy, we can find a point on our curve that's within delta in the x direction and has the exact y value we're looking for. Here I've plotted one wave, one oscillation of the graph. I'll assign this wave to take care of points xy and deltas, where the points fall within its bounding rectangle and delta is less than the width of the wave. If we have a point xy in this rectangle, I'll want the nearby point on the graph to come from this wave. Again, this nearby point will have the exact y value we're looking for, and the x values will be within delta of each other. So in particular, in order to get this to work, we're going to need to find waves whose bounding rectangles cover all points in the plane with arbitrarily small widths. We're going to need to be able to find an oscillation, find a wave that covers our point xy and whose width is less than delta. First, in order for our graph to get close to our point, we first need to look far enough out on our parameterization so the graph actually covers the relevant x value. T has to be at least as large as the absolute value of x in order for our L function, t sine of t, to actually achieve x as a value. We might not get close enough to our point the first time t sine of t gets near x, but if not, we can always skip forward along the curve to the next time t sine of t gets near x, or the time after that, or so on and so forth. We also need to make sure that our wave achieves the desired y value. Working out the exact max and min achieved by the graph over a particular interval is a tricky piece of calculus, but we can set some upper and lower bounds once we know what t values we're looking at. For this particular wave, we're going between 2 points where r of t equals 0 because we're plugging in a multiple of 2 pi into sine. In particular, we're looking at values of t between the cube root of 2 pi k and the cube root of 2 pi k plus 1 for some natural number k. And so with some reasoning about inequalities, the peak of our function is going to happen somewhere between y equals the lower t value and y equals the upper t value. This won't happen exactly at the point where sine of t cubed is equal to 1, but that's a good way to start thinking about where this point is. Again, you need to use some calculus in order to figure out what the exact maximum value is. And so, once we go out far enough that our t values exceed the desired y value of our point, our oscillations and their bounding rectangles will cover our point in the y direction. The hardest part is making sure that the width of these waves and their bounding rectangles is less than our desired delta. Again, we just have to make sure that we're looking far enough out in our curve. In the grand scheme of things, our oscillations get narrower and narrower as t gets larger and larger. The limit of the width of these waves as t approaches infinity is 0. The exact width is going to be given by this gross formula here, which I got by plugging in the t values we got for our endpoints into the L of t function and computing their distance. This is just f of k plus 1 minus f of k for this gross function f here. So by the mean value theorem, the one-dimensional mean value theorem, this is exactly f prime of c for some c between k and k plus 1. Basic calculus gives us this expression for f prime of c. And when we take the limit of this expression as c approaches infinity, and that's going to happen as k approaches infinity, using the sandwich theorem, we can essentially ignore the cosine and sine terms. Those are going to be sandwiched between -1 and 1. And it's actually not that bad of a limit to take once we do that. Anyway, the limit of this expression as c approaches infinity is 0. And what that means is that there's some t value such that as long as we go out past that particular value of t, the wavelength, the horizontal width of our wave, is always going to be less than any delta that we want. So given our delta and given our point xy, we can find a point on our graph that's close to our point xy by going out far enough along our curve, looking at large enough values of t that we're covering the appropriate y values. We need to go far enough out along so that each wave has width less than delta, and then we need to keep going until we get an oscillation whose bounding rectangle also contains the right x values. Beyond a certain point, t sine of t will achieve the desired x values in a roughly periodic way. So this will give us a wave whose bounding rectangle contains the point xy, and whose width is less than delta, and finally we can pick a point on that wave that has the exact right y value, and because the width of the wave is less than delta, the x-coordinate of our point on the graph will be within delta of x. Again, our goal here is to reduce a two-dimensional search for some point xy with f of xy strictly less than 1 to a one-dimensional search for some t with f of t sine of t sine of t cubed being strictly less than 1. Let's take a look at the Pell equation example again. Here I visualize the points where f is strictly less than 1. Since our f function is continuous, the points where it's less than 1 actually form these little ellipses around the roots of the Pell equation that we were searching for. So again, because our parameterized curve is dense in space, it will eventually fall into one of them. However, these ellipses are very tiny, especially as we get far away from the origin. So there are a lot of near misses. We see one here, and a really close near miss 42.5 waves in. But again, because this curve is dense in the plane, we will eventually hit these ellipses. I found an intersection 177,292.5 waves in, as we can see here, which I believe is the first point where f is less than 1, but I may have missed an earlier one due to numerical imprecision. But the point is that this curve will eventually find not just this point where f is strictly less than 1, but every region where f is strictly less than 1, due to its density in the plane. Of course, we need to be able to search higher dimensional space than just 2 dimensions. Let's say we wanted to encode a quadruple x, y, z, w using an appropriate pairing function, an appropriate bijection from pairs of numbers to single numbers. We could first encode the pair zw as a single number, call it p. Then we encode the pair yp as a single number, say q. Then we encode the pair xq as a single number, call it t. Then t contains all the information we need to recover our original quadruple. We unpair t to figure out x and q, then unpair q to figure out y and p, and finally unpair p to recover z and w. Again, we don't have an appropriate bijection from pairs of numbers to single numbers, but we're close. Using our Richardson unpairing-like functions, we can encode our quadruple x, y, z, w by first looking for some p such that r of p equals w and L of p is within delta of z. Then we'll look for some q such that r of q equals p and L of q is within delta of y. And finally, we'll look for some t such that r of t equals q and L of t is within delta of x. And so our t will encode a point that's near to x, y, z, and w. We can unpack it like this, and L of t will be within delta of x, L of r of t will be within delta of y, L of r of t will be within delta of z, and actually r of t will be exactly w. So we'll get a point that we can get to be arbitrarily close to the point x, y, z, w. And again, since every Richardson function, all of our capital F functions are continuous, that's all we need. We can convert a search for an x, y, z, and w with f less than 1 to a search for t with f of L of t, L of r of t, L of r of t, and r of r of t being strictly less than 1. If there's a solution to be found, even though our search doesn't cover all possible points in R4, since our search covers a dense set in R4 and our function is continuous, it will find solutions if they exist. And again, we can then do the absolute value trick to turn this into the question of whether a term is not identically zero. And of course, there's nothing special about having 4 variables here. We can do exactly the same sort of construction for arbitrary numbers of variables. So to summarize, we can't possibly have an algorithm to tell whether 2 single variable Richardson expressions are equivalent. For the sake of contradiction, suppose that we did have such an algorithm that could tell us whether 2 single variable Richardson expressions are equivalent, and we have some sort of Turing machine T, and we want to know whether T halts. First, we can convert our Turing machine into a corresponding Diophantine equation, P equals 0, that has a solution if and only if the Turing machine halts. Then we convert P into a multivariable Richardson inequality, f is strictly less than 1, that will have a real solution if and only if the original Turing machine halts. Then we convert our multivariable Richardson inequality into a single variable Richardson inequality using our unpairing-like functions that will have a real solution if and only if the Turing machine halts. And finally, we asked the algorithm that we supposed existed if the absolute value of f minus 1 and f minus 1 are equal for all values of the variable. They won't be equal if and only if there's a solution to the inequality, which is if and only if the original Turing machine halts. Together, this would give us an algorithm for solving the halting problem, which we know can't exist, contradicting our assumption that we could have an algorithm for determining whether 2 single variable Richardson expressions are equivalent. Now, this rules out a universal algorithm for equivalence of Richardson expressions. We don't have an algorithm that works in all cases, but we do have heuristics, algorithms that only work in specific cases. Again, we can easily tell if 2 polynomial expressions are equivalent, but we can't have an algorithm that handles all of the cases. But of course, the situation is more dire than that. There are individual Turing machines with particularly thorny halting problems. A Turing machine that hunts for an odd perfect number or a proof to some other open math problem. Or a Turing machine that hunts for a proof that ZFC is inconsistent, which never halts, but ZFC cannot prove never halts. And if we have one of these Turing machines, we can, through this straightforward process, it's kind of tedious to apply in practice, but it is a straightforward process, convert our Turing machine into an equally thorny question of equivalence of Richardson expressions. Our odd perfect number hunting Turing machine gives us Richardson expressions that are equivalent if and only if there are no odd perfect numbers. Our Turing machine that hunts for a proof that ZFC is inconsistent becomes Richardson expressions that are equivalent if and only if there's no proof that ZFC is inconsistent. In other words, assuming ZFC is consistent, then these expressions are equivalent but can't be proved to be equivalent in ZFC. In short, trig identities and really trig inequalities are hard. So thanks for watching. Please leave any questions or comments you have down below, and be kind to each other.